Good morning and good afternoon, or whatever your time zone is, everyone. And I'm glad people who are in the middle of the weekend and early in the morning today have joined us. And I'm very glad that David joined us today. So we have today a presentation by David Waddington from University of Sydney, and this is going to be about a pretty interesting topic, at least to me, about combining Linac and MRI. As far as I understand, maybe there's going to be some other topics in there, but I've heard a lot of that project, and I would be really glad to hear something about that. So if you have any questions during the talk, David, do you want questions to be asked during the talk, or?
I mean, if people want to jump in, and maybe I'll let you, if we get a little too far off track with questions, do you know what I mean? I'll let you.
Yeah. Okay.
Yeah.
So
yeah, if people ask questions during, that's fine. Yeah.
Yeah, just raise your hand in Zoom or type them in the chat, and I'll sort of interrupt David at some comfortable point where you would either ask your question yourself or just I will read your question from the chat. And I would ask everyone except for the speaker to turn off their cameras and sound, which I will do myself too. So David, with that, I think you're welcome to start. Thank you.
Okay, thank you for the introduction. So, yeah, I'm at the University of Sydney and working on, as Mikhail said, the Australian MRI-Linac program. So aiming to combine radiotherapy with the incredible imaging power of MRI. But for today, I've kind of titled this talk kind of Deconstructing MRI, preferring to look at it through a lens of how do we create these new imaging technologies. And specifically, I'm going to be talking about my work with low field MRI and also with radiotherapy. So let's get into it. So diagnostic MRI, we love it. We typically, almost always in a clinical sense, image protons. And it's really been restricted to date to the diagnostic imaging suite. However, in the last few years, there's sort of been a lot of re-engineering of hardware in addition to the physics of the image acquisition and the image reconstruction to push MRI into new frontiers. And so a couple of examples of that are the MRI-Linacs, combining an MRI scanner, in this case a split bore MRI scanner, with a linear accelerator or Linac to use X-rays for treating cancers. And also, as I'm going to be speaking about, really kind of stripping back the MRI scanner to low field MRI to make portable and inexpensive images. So let's jump into the radiotherapy and start though, of course, with the question of why does radiotherapy need MRI? Well, as pretty much any 8-year-old could tell you, X-rays are for imaging bones. And in standard radiotherapy, X-rays are the mainstay of the imaging, but almost all the tumors that are treated are soft tissue. So really what we have is a case of the imaging in conventional radiotherapy systems not being up to the task of imaging tumors, which is what we want to treat. On the other hand, MRI is amazing for imaging soft tissues. And so we compare here, say a CT of a prostate cancer, we can see sort of this sort of even grey tone with the CT or the X-ray. And then we have this really fine structure in the MRI scan of the same prostate. You can sort of see the tumour based in around here. I think my mouse cursor is different places on my two monitors, but anyway, you can see the tumour indicated down here. Anyway, so really what we want to do is combine MRI with radiotherapy. So what do we need to do that? Well, on the one hand, it's conceptually quite simple. We need an MRI scanner, this beast on the left, and we want to combine it with a giant rotating steel thing that creates X-rays. And conceptually that's simple, but in practice, big hunks of steel really don't like being in magnetic fields. But the motivation is strong. And so over the past few years, there's been a lot of commercial drive to do this. And Globally, there's actually 2 commercial MRI-Linacs that are being sold now. One of those is the Meridian by Vure, and so that was first used in January 2014. At that point, it was a cobalt source rather than a linear accelerator, but the technology is to date still fundamentally the same. And on the other side, from a combination of Elekta and Philips, there's a machine called the Unity. So the real difference between these two is that the Meridian operates at 0.35 Tesla, whereas the Unity operates at 1.5 Tesla. So a higher imaging quality, but at much greater expense. And there's around 100 of these systems in the world combined today. In Australia alone, we've had a company invest a couple of $100 million in them in the last couple of years. So they're really taking off. Now, these 2 commercial systems are there, but so where do I and where does Australia fit in all this? Well, we have, where does Australia and where do I fit in this? Well, we have something called the Australian MRI-Linac program, which has been an MRI-Linac research program for nearly 10 years now. And so what our program did was to build early on our own prototype system by combining a fixed source Linac with a split bore MRI system at 1 Tesla. And you can see here there's all sorts of institutions as part of this program, and really trying to look at and see how do we use the MRI to adapt treatment, and how do we innovate with the device and more accurately target cancers with the radiation that we're using to treat tumours. And something that is a peculiarity of our system, and why it's very much a research system, is that you'll see that we don't actually have this rotating gantry to manipulate the X-ray beam. So for most of our research, we actually rotate the patient to achieve different angles between the Linac and the patient, which is a bit out there, but it's what we're doing. So I'll give you a quick view of what it actually looks like in practice. We've got the Linac on the left, and then we've got, this is the MRI scanner inside with a little MRI coil there. Yep. And really, like, as I said, it's a research scanner. One of the real strengths, possibly also a weakness, but strength of the system is we have a lot of flexibility to how we position patients, how we image patients. So we can do horizontal treatments, we can do vertical treatments, and we can orient the patient in any particular way along the B0 magnetic field. Now, at the University of Sydney, so we call the ImageX Institute, we're really about how do we more accurately personalize the targeting of these radiotherapy systems, and how do we adapt treatments in real time. And so these are a few little things here that I'm going to be talking about. So real-time MRI-based adaptation, MRI-based radiation dosimetry, and some just touch on clinical trials that are happening, but I'll jump into that. And we've actually got at the University of Sydney a growing team now, so 7 of us working on this project. So let's get into the real research and development. Now, one of the main bits of technology that we want to build for these MRI-Linacs is a way to target moving tumours. Now, the reason we want to do that is that we want our X-rays to hit the tumour. We don't want them to hit the healthy tissue around the tumour, because that causes all sorts of complications and just damages healthy tissue, and we don't want to do that. So we have this tool that's known as a multi-leaf collimator that can, in real time, steer a radiation beam from a Linac. And so what we want to do is take an MRI scan and identify a particular target and be able to track that target in real time to adapt the beam. So jumping forward to, in the context of the prototype system, what might this look like? You have a patient, the treatment beam, and then you have these individual little leaves that are made of tungsten and absorb the X-rays, adapting their shape to absorb the X-rays and shape the treatment beam.
Sorry, I had a question. Does this leaf collimator work that fast that it can follow the breathing of a person, so that those leaves can move?
Yeah. So these leaves slide in and out on kind of length scales of millimeters per second. They are not super fast, but they can move fast enough for respiration. One of the challenges that we have is, so I should say on a conventional system, so a standard Linac, they're definitely fast enough to track respiration. I'll show you in a sec some actual data. But when you put them in a magnetic field, one of the real challenges is actually with all the motors and whatever else that drive them, minimizing that interference. But the answer to your question is yes.
Okay, thank you.
Yep. All right. Okay, so as I guess you were going there, a little bit of clinical context for what's going on here. We can imagine that, for example, we're imaging a tumor here as outlined in blue. And you can see here, this is what we call a centrally located tumor. So it's really close to some of the cardiac substructures, and those cardiac substructures are really radiation sensitive, and it can cause all sorts of treatment-related toxicities if they're irradiated by accident. Now, from a motion and a speed perspective, okay, our cardiac motion is about 60 beats per minute, or about a hertz. Our respiratory motion is about a breath every 4 seconds, so 0.25 hertz. And what we want to achieve here is kind of millimeter scale accuracy. And so this is, I'm just going to show you some work that was led by my colleague Paul Liu at the University of Sydney. And what we did here was really trying to quantify using this MRI to track 2 targets in real time with the MLC as a measure of proof of concept for what it might be like to track tumors that are moving independently, and in this case with respiratory type motion. And so in this experiment, for those of you interested in the MR, it's a Trufi acquisition, a Cine MRI, but I'll show you what's actually going on here. What we have is this motion phantom. And so you have 2 little tumors, fake tumors, and these are printed out of a 3D plastic that's MR visible. And they're moving with a program to actually a patient's true respiratory trace and the kind of motion that you would expect in the lung. And then based on the Cine MRI, so which is scanning on this phantom on the left, using an algorithm based on segmentation and track the position of the tumors, they're extracted in these 2 little boxes here, and they get sent across to the MLC tracking algorithm that moves the leaves to track those positions. And then on the 4th step here, what we actually have is an EPID, is an electroreporter imaging device. So what that actually does is it detects the radiation that makes it through the MLC leaves, and segmented out here in the blue on that image, we have there's a slight discoloration where these little fake tumors are absorbing some of the radiation. So using this EPID, we're actually able to measure how accurate the tracking technology is. And so if we look at some data to do with that, what we have here in the solid line is the target position. And in the dotted line, we have the aperture position. So the lag between those 2, the delta T, is the latency of our tracking. And so via the latency of that tracking, we see that we actually have about 330 milliseconds between the true target position and the how quickly we adapt to that. Now, when we look deeper into what is this 330 milliseconds, about 130 milliseconds is based on how fast it is to move those leaves, as well as the processing time to extract their positions. But the vast bulk of the acquisition is, or 200 milliseconds, is the MRI. And so accelerating this MRI is something that we're particularly interested in. And in this case, you'll also notice this is quite a low resolution scan, small field of view, which is probably not realistic for what you would actually want to do in a patient. You want to go high resolution, bigger field of view, so you can really encompass everything that's going on. So this long latency of the MR imaging leads into the next bit of the process. And That's about trying to enable imaging with radial sequences with fast reconstruction. And so for those of you that aren't familiar, that when you're performing MRI, usually you're faced with a choice about how you perform your position encoding, or sorry, your spatial encoding, or your frequency and phase encoding via your gradients. And almost always for everything, you use what is known as Cartesian encoding. So these parallel lines in K-space. But it turns out that when you're performing cardiothoracic imaging, what you really want to do is use something that's known as radial MRI, or even golden angle radial MRI. And what that does is it manipulates the gradients in such a way that the data that you acquire lies along these spokes in K-space. And what you get as a result of that is repeated oversampling at the center of K-space. And what that does is it suppresses any of the phase shift errors that occur via the motion. And on top of that, we can use compressed sensing reconstruction at arbitrary undersampling factors with this radial acquisition. And what that means is we don't need to acquire all the data as we often do in a Cartesian context, although there are ways around that. So what we want to do is acquire this radial MRI data. But then we have a problem, which is that with radial data, what we have is non-uniformly sampled data in the frequency domain, and we want to map that data to uniformly sampled data, so image data in the image domain. And now the normal process of doing that, this is compressed sensing with an iterative reconstruction, an enforcement of sparsity constraints in what's typically known as the wavelet domain. And these image reconstruction processes work really well, but they're really slow. So to recap, we want to do radial MRI, but the normal way to reconstruct radial images is slow. But on the other hand, neural networks are really, really fast. And it turns out that you can do image reconstruction in a single forward pass with these neural networks. So what we're proposing to do is using neural networks to perform accurate and fast image reconstruction to enable this dynamic tumor tracking. Now, there are several neural network options to perform this reconstruction. There's AUTOMAP, there's Deep Cascade, there's Dagon. There's a lot of neural network reconstruction approaches. I'm sure you've all seen many neural network things all over the place by now. But in this context, what we're going to use is something known as AUTOMAP. And so what we want to do, image the tumor, reconstruct fast, work out where the new location is, and adapt our MLC. Now this AUTOMAP also stands for Automated Transform by Manifold Approximation, was developed by our co-authors at the Martinos Center and reported in this Nature paper. And what AUTOMAP does is it takes the raw sensor data, so that data in the case-based domain, the radial case-based data in our case, and it transforms it to the image domain via this manifold approximation, which is a forward process. And now when we implement this here in this neural network approach, so for those of you that are familiar with neural nets, it's a couple of fully connected layers followed by an autoencoder for denoising. Now to train this model, we actually trained it on random images that we sample to this undersample radial data. And so the reason that we want to use random images is to encourage generic representations of images in raw synthetic case-based data. In this case, I've shown you a generic representation of a puppy. We then use this case-based data and images to train our reconstruction network. So here I'll show you a typical training and validation curve. Basically, the epoch is the number of iterations of training through the full data set. And you can see that the validation cost comes down quite nicely and then begins to overfit. And the reason for this overfitting is because of synthetic noise in the data set. And that takes a couple of hours. Okay, but we've trained our neural network. Now we want to test it. We want to perform reconstruction. And what we find and what we use for that is this digital phantom of this cardiothoracic phantom. Oops, sorry. Now to show you what so we undersample the data from this digital MRI phantom and to look at a complete sort of non-uniform fast Fourier transform, absolutely not the way that you would want to perform reconstruction. You can see you get some quite nasty reconstruction here, so a root mean square error of nearly 20%. But then we go to our more advanced approaches, and what we see is that AUTOMAP has an accuracy of very similar to the most advanced wavelet-based compressed sensing reconstruction approaches, but it's much, much faster. So in this case, 50 milliseconds or 2 seconds. Okay, so at this point, we're still in the process of getting those radial sequences working on our MRI-Linac, but as a proof of principle, we have here some cine MRI Cartesian data acquired off our MRI-Linac, which we then reconstruct with AUTOMAP. So that's where we're up to with that. So aside from sort of the tracking approach of adapting to motion in these radiotherapy treatments by MRI, one of the other things we want to do is use MRI to detect radiation doses. And so one of the ways that we can do that, if we look at this here, is via using a radiation sensitive gel. And so the idea is that you would image this gel with cine MRI or some other different type of MRI and detect a contrast, as in this case from the radiation beam through a gel, that gives you an idea of the dose or the radiation dose that has been deposited. And so these things are really useful for dosimetry and also in verifying clinical treatments before you proceed with them. And so what I'll show you here is some work that we've done with Macquarie University, which is another university in Sydney as well, with what's known as a MAGAT dosimeter. Now, these dosimeters are essentially a gelatin. So this gelatin gel that is a methacrylic acid mixed with gelatin and then with an antioxidant in there to stabilize it from oxygen messing up the reactions that you want to detect. And what happens is that gel, when it's exposed to radiation, it polymerizes. And the polymerization changes the relaxation times of the water nuclei in that gel. And relaxation times of water nuclei are what give us all of our contrast in MRI. And so what we can do then is we can look at turning that change in contrast, in this case it's a T2 change, and we can see that we can map that onto a radiation dose and see the dose that accumulates with each of these different treatment beams. So as you look across here, you see that this head phantom that we're imaging has been exposed to beams coming from different directions. And the idea would be that you have a tumor in the center here that receives the full 5 gray, whereas the rest of the brain is spared from the rest of the healthy brain is spared from the lower dose. So to give you a little movie of what this might look like, here we're looking at 5 different slices through the brain. And this central slice here is where we really want to focus everything in. And so using this dosimeter, we're actually able to using MRI, verify where the radiation dose has been deposited. Now, as for clinical trials of this system, I don't really want to speak about it too much, but I just wanted to say that with our system, we're really at the point that we've got ethics approved and we're due to start really soon on patient recruitment of these different systems. And really probably the first clinical site that we'll be treating is whole brain treatments or brain metastases. And one of the reasons for that is it's a very simple alignment process where you have parallel opposed fields. And that means that you only have to direct the radiation from 2 angles, as well as the fact that it's a simple alignment, a simple test case, rather than a fully fledged testing all of these different adaptation technologies I've been speaking about. So in terms of our MRI-Linac, MRI radiotherapy work, we're really looking at moving forward with real-time tracking and new approaches to make that faster. Really looking at ways of imaging MR dose, and moving forward, we're really looking at also different biomarkers that respond to that dose, and moving forward with clinical trials. And I might just pause here for a second, say if people have questions about the radiotherapy work.
Thank you. I think we have a question from Ekaterina Brui, right?
Yes. Hello. Thank you very much. I'm sorry for interrupting. I just wanted to ask about this dosimetry. So I guess that this phantom does not represent the characteristics of the brain in terms of radiation, like how it accepts the radiation. So the dose which this phantom gets, it cannot be the same as the brain gets, or maybe I'm wrong. So do it make some calibration?
No, so that's yeah. No, that's a fair comment, and I think so. I would say that the phantom that is there does not accurately represent the dose that would be deposited were that somebody's head. Part of the treatment planning process is that you look at the attenuation that you would expect of X-rays based on every treatment has a CT planning element to it, and you adapt for that. And so you essentially work out how much the X-rays would be attenuated, and the treatment is planned around that. In this case, it's unique to that phantom, but we do have a subsequent phantom that we're now working with for the clinical trial that I showed you, where the anatomy is very much realistic with respect to a human brain. And really, I think the most important bit there is the idea of having the skull, because that attenuates much more highly than the difference between a gel and the human brain. Does that answer your question?
So as I understand, you just use it just to see to see where this beam will be focused, or for what purpose?
Yeah, it's a proof of concept, or also I would say more a quality assurance. So there are other, it's more of something that you can do before you put a real patient in there to check that everything is working as you expect it to be working. And we have now, since that work was done that I showed you, a higher, I don't want to say higher quality, but a much more expensive phantom that is more representative of the human anatomy, that will give a closer check that things are working as you would expect.
Okay, thank you. But the concept is really interesting. Thank you.
Okay, thank you. I had a question also about the dosimetry. How fast does it work? Because in this one you showed you expect the polymerization to happen and the relaxation change to happen, then you expected to notice the relaxation change. But in the other one that you showed before, I think it was the different method. Does it work on the same principle where you can
So yeah, it's a good question. I'm not the chemist on that paper, but I'll do my best job of answering. So there are different types of gel dosimeters, and there are lots of different aspects that you have to think about to do with the chemistry. In this case, it's one of the most reactive polymerization reactions, I guess. And so it stabilizes very quickly. So after you expose the radiation, it then stabilizes on the time scale of seconds. And that means that in our case, we're imaging it on a kind of like I think it's a 44-second window. Each of those frames was 44 seconds apart. There are other dosimeters, for example, though, also based on polymerization, where you expose them with radiation, and then you can watch a kind of reaction plateau over the time scale of an hour. And then there are also separate dosimeters, again, that are based around the idea of having iron in its ionic state and creating an Fe2+ to an Fe3+ reaction. And because Fe3+ is so much more paramagnetic than Fe2+, that causes a really significant change in T1. So there are different approaches. The chemistry of it is really challenging. On top of that, something I didn't mention is just really ensuring that you have temperature stability as well, because reaction kinetics change based on temperature, and that will give you a can give you errors in the dose that you read out.
Okay, so we don't have any more questions for that part, I think.
Yep, cool. I'll keep forging ahead then. So pivoting from radiotherapy, I'm going to talk about some other work that I've done, which is around low field MRI. And so we want to start with the question of why does MRI need low field? Well, MRI is really expensive. It's one of the most expensive imaging modalities, and typically it's around $1 million per Tesla magnetic field. On top of that, these scanners are really heavy. A 1.5 Tesla system can easily be 5,000 kilos, 5 tons. And when we go to lower magnetic fields, we reduce both these problems. We make scanners more portable. So especially permanent magnets can be lighter, and then electromagnets can be really, really light. And yeah, and so what we can do then is build MRI scanners that much cheaper and able to go to all sorts of different places. And so what we're really imagining with this sort of low field MRI is something like what we'd call the battlefield MRI, where someone has an injury out here, they get airlifted up to a helicopter and they get some sort of preliminary assessment. They then go to a field hospital, and then if necessary, they can be taken back to a real hospital. And the idea is to have sort of portable systems in each of these locations. Now, on top of that, something I'll touch on is the idea of imaging brain injury via free radicals, but really the focus is this low field MRI. So, okay, going to low field MRI, we understand that will make MRI cheaper, but of course there's going to be a drawback. And that is that MRI signals are already very small. So going back to basics, when we talk about where does an MRI signal come from? Well, we put a proton, in this case, the hydrogen nucleus of this water molecule, in a magnetic field, and we open up a Larmor splitting. Now that has a resonant frequency at a characteristic, a frequency that's characteristic of the gyromagnetic ratio in the magnetic field. But the magnitude of the signal we measure is also based on the nuclear polarization. And so that nuclear polarization is also characteristic of the gyromagnetic ratio and the magnetic field strength divided by the thermal energy. And so that, or magneton times the magnetic field, is incredibly small. And in conventional MRI, where we're talking about sort of 1.5 Tesla, this nuclear polarization is about a ppm, or 1 part per million. So what that means is that for every 1,000,001 nuclei that are up, we have 1,000,000 nuclei that are down. So we're only measuring about 1 in 1,000,000 nuclei. So MR signals are already very small, and by going to lower magnetic fields, that scales linearly, the polarization. So we're going from small to even smaller. So naively, what you might say is that, okay, we have this smaller polarization, and you can do some calculations and you can show that the signal to noise scales roughly as the magnetic field strength to the power of 3/2 based on some other factors in the MR acquisition. And so if we go to an ultra low field scanner, in this case in our lab in the Martinos Center, Massachusetts General Hospital, where I've worked quite a bit over the last few years, it's about 200 times smaller than a clinical scanner. So if you plug that number into this signal to noise equation here, you find that the imaging time, which scales as signal to noise squared, might be about 8 million times longer than you expect in a clinical system. So the question is, can we do MRI at 6.5 millitesla? Bearing in mind that the reason that we wanted to proceed with this madness is that Ideally, we can make a lightweight portable scanner that might be around $50,000 in cost. Now, before we do that, what I want to do is point out a couple of things. One of those is that high efficiency MRI sequences, so the process through which we acquire the information and manipulate the spins, are relatively easy to implement at low field thanks to the high absolute magnet homogeneity. So to explain a little bit more what I mean there by that, this plot here shows the signal that you might expect from a spin based on its offset from the expected Lamont frequency during acquisition. In a perfect imaging system, we would love a horizontal flat line across the top here. But in practice, what we have is this small plateau between -10 and +10 Hertz. And what that means is that for us to image successfully in our system, we need all our spins to be located in this region. Now, in a 1 Tesla system, if we have inhomogeneity in the magnetic field of order 1 part per million, that means that we have a 40 Hertz spread of the Lamont frequency across our spins. So we've used up all this space. At 6.5 millitesla, that same fractional inhomogeneity is 0.3 Hertz. So that means that we can go up to 100 parts per million inhomogeneity, so a much, much more inhomogeneous field, and still use these high efficiency sequences that have these characteristic curves, in this case, this balanced steady state free precession. Now, on top of that, developing coils, which I know is work that many of you do, is quite different at low fields as well. And one of the main reasons for that is that SNR at low field, and especially ultra low field, is Johnson noise limited, not body noise limited. And so by that, what I mean is that most of the noise that you detect in your acquisition comes from the coil rather than coming from the patient. And what that means is that you can keep building a higher and higher Q coil to image that patient. Until, of course, you actually run into a problem, which is that our gradients in MRI, our readout gradients, actually spread the spins in frequency space to perform frequency encoding. And you can build coils that are too high a Q such that you only detect the spins in the middle of your sample, as illustrated here, rather than the ones around the edges. And so really what I'm going to say here is that we put a lot of work into optimizing coils for this magnetic field strength and really getting the best balance we can of Q factor to the readout bandwidth that we actually need for our system. So when we put that together, in this prototype system at the Martinos Center, we're able to perform clinically useful imaging of the human brain in just 6 minutes. And so again, it's like 6.5 millitesla in 6 minutes. So while I was helping out with this work at the Martinos Center, the PI, who's Matthew Rosen, started talking with this guy on the left, Jonathan Rothberg, and they were kind of inspired to found a company around this idea. And 5 years later, so last year, this scanner came out, which is the Hyperfine Research MRI scanner. It operates at 64 millitesla, so a factor of 10 higher, but still very low field. And it's actually been FDA approved and has now been used for imaging the human brain, including of COVID patients and stroke patients in the ICU. And one of the great things about this scanner is that it's still limited to the hospital, but you can actually wheel it to the patient in their bed. And this little yellow bar here kind of pops out a little bit, but that's actually kind of where the 5 Gauss line is. So it's nothing like the risk to projectiles and electronics that you'd expect of conventional systems. Now, beyond Hyperfine, there's also another company known as Promaxo, and they've developed this kind of custom, also portable system for prostate imaging. So for urologists to have in their offices or on site to get the information they want. Now, so portable MRI, low field MRI is a thing. It's taken off. It's not all great. one thing that we've been wrestling with is the fact that traditional contrast is often not so feasible at low fields. So I spoke about the fact that we use these accelerated sequences. Now, one of the things that means is that spin echo scans or your typical contrast sequences can often take a long, long time to acquire at low field. But if you use balanced steady state free precession or the high efficiency sequence I've been speaking about, what you find is that you lose your image contrast. And for those of you that are really interested, the reason for that is that at low field, the T1 and T2 times converge. That's a generic property of all systems. And what that means is that for the BSSFP acquisition, which is weighted by the ratio of T1 on T2, you get this convergence in values. Now, one of the things that that we've worked with is looking at spions or superparamagnetic iron oxide nanoparticles as a new type of contrast agent specifically for low field. And now these are something that have been used previously at high field, but taking them into the low field domain, got an example of some here. What we find is they're kind of ideally suited for this application. And the reason for that is that they have this nonlinear magnetization that means that they have an absolutely huge magnetization at ultra low field compared to other contrast agents such as ones based on gadolinium. Now, what this translates to on top of various factors around correlation times and such is huge what we call R1 and R2 relaxivity effects. So GAD DTPA, gadolinium DTPA is one of the clinical standards for MRI, one of the common contrast agents for MRI. You can see these values here of 7-ish per millimolar per second compared with 300-ish per millimolar per second for the spions, the iron oxide nanoparticles. So what that means is they're detectable at much lower concentrations. So in a proof of principle work that I led here, we're showing that these contrast agents give us, in a rat model here, give us really good contrast of the liver, the lungs, and the kidneys. And in the corresponding gadolinium test, we don't see image contrast. Now, on top of that, if you're super interested, there's also a bunch of susceptibility-based contrast effects that you can use. Now, something a little bit more out of left field that opens up to us at low field is generating contrast through something known as the Overhauser effect. Now, for those of you that haven't seen it before, what the Overhauser effect does, it's a hyperpolarization technique that transfers big electronic spin polarizations to small nuclear spin polarizations. So to put that in, to explain how these high nuclear polarizations are generated, I'm going to show you this little schematic, which is not to scale. But what I have here is a bunch of paired electron and nuclear spins in the little energy level diagram. And what you see is that between the first two levels, we have a nuclear spin flip, so a very small energy splitting, so of order the nuclear long mole frequency. And then up here, we have a big energy gap when we have an electronic spin flip. And what that means is that the polarization between the spin flipped electronic states and the nuclear states is very, very large. And depending on field and temperature, it can be up to 100% at low temperatures. Now, this splitting between the states on the nuclear side is this same creation of the 1 part per million polarization I spoke about earlier. So that really kind of stops you getting the polarizations you want. But what you can do is you can drive that electronic transition. So with a coil that is resonant at the electronic frequency, and that equates the populations in the two states. And then just by the nature of dipolar coupling between the electronic and the nuclear spins, what we see is that one of these two cross relaxation processes dominates. And what that does is it forces the spins from this state to over here. And when we do this, what we find is that we've transferred that electronic spin polarization to the nuclear spin polarization and gotten a really big spin polarization that we can use for imaging. So In practice, what that means is a tiny NMR signal becomes a giant NMR signal when you drive these electronic spins. So why isn't this done more commonly? Well, at clinical magnetic field strengths, you run into a problem early on, which is that the electronic resonance frequency is of order 30 gigahertz per Tesla. If you look at 30 gigahertz, that is extremely strong absorption. It's a microwave frequency, and that means that there's extremely strong absorption by water molecules. So you'll cook your sample or you'll cook your person, and that's not something that we like to do clinically. But if we go down to these low magnetic fields, we see that there's almost no dielectric loss, and we can actually, so when we drop down to 6.5 millitesla or the very low magnetic fields, we can actually perform this process. So to do this, what we do is we build some nice custom hardware. In this case, we combine an NMR or an MRI coil operating at 276 kilohertz, which is our MRI hydrogen frequency at 6.5 millitesla. And with that, we put in an EPR coil or an electron paramagnetic resonance coil, in this case at 140 megahertz. And so we use this coil to drive electronic spin polarization that we can image with this coil. And put a lot of work into optimizing that. I won't go into it now. But let's look at this in an in vivo context. What we have here is a healthy rat, and what we want to do is probe. This is a model that we are in the process of developing for stroke imaging, but in this case, it's a healthy rat where we inject a free radical known as tempol. So a free radical is a source of these electron spins that we're going to image. And so in this case, what we do is we inject tempol into this hemisphere of the brain, and then with conventional MRI, we see nothing. But then if we turn on our Overhauser MRI, we see this bigger enhancement, in this case, a factor of 4 in the ipsilateral hemisphere of the brain due to the presence of that free radical. And if we plot this as a function of time, we can turn it into something that tells us about the uptake of the contrast agent. So what other, okay, so that's a way of imaging, a new way of imaging that we can do at low field and ultra low field that we can't do at high fields. What else is open to us? Well, just quickly, and this is the last thing I'm going to show you, just some work that we've been doing looking into the idea of nanodiamond theranostics. So for those of you that don't know, nanodiamonds become enormously interesting as a theranostic agent. And what I mean by that is the idea of combining some sort of therapeutic that treats with some sort of diagnostic agent that we can image. And the reason that nanodiamonds become promising as a theranostic agent is because it has optical centers in it, typically the nitrogen vacancy centers that fluoresce really strongly. And that has enabled all sorts of interesting results on subcellular length scales that are optically accessible. On top of that, you can functionalize the surface of nanodiamonds with different drugs, including chemotherapeutics, to deliver therapeutic payloads. But because of the optical accessibility of these nanodiamonds, there's still no way to, of these nanodiamond color centers, the fluorescent centers, there's no non-invasive method to image them. And so that's something we kind of came up with the idea here is, okay, nanodiamonds have all sorts of free radicals around their surfaces. So can we couple the electronic spins on the surface of the nanodiamonds to hydrogen nuclei in solution? And went away and did some modeling, and we found actually this coupling is kind of optimally strong at ultra low field as well. And that's based on the correlation times of these things in solution as they move around each other. And then when we do the experiments, so we put nanodiamonds and water in solution, we find that we can create this Overhauser effect and get an enhancement of a factor of 4 again in the effect. So just showing that we can actually use this as a way to image nanodiamonds non-invasively. We mocked up a little phantom here of nanodiamonds in solution and water in vials here. Our conventional MRI shows us no contrast, as we said before. We turn on our Overhauser effect and we see a big contrast between the nanodiamond and the MRI. And so the nanodiamond and the water vials. We can take a difference image here to show the presence of the nanodiamond. So really talk about what's going on here. Low field MRI has arrived. It's all about creating new hardware and new acquisitions, but on top of that, it's about creating new forms of contrast, and we're really looking into ways that we tailor these nanodiamonds to improve the contrast signals that we were talking about, and ways that we can functionalize our iron oxide nanoparticles to deliver to certain sites and further this work. So in conclusion, by re-engineering the MRI scan and moving out of the diagnostic suite, we can enable new technologies in cancer imaging and emergency care. So new approaches to MRI hardware, image contrast, image acquisition, reconstruction are really needed if we want to keep pushing MRI forward in these new spaces. So specifically in the work that I've been talking about, MRI-Linacs for cancer treatment and low field MRI for point of care imaging. And just want to finish by saying thank you to many of the people that have made this possible and the institutions as well. Yeah, and that's it really. Open the floor to questions, I guess.
Okay, thank you, David. That was actually a very amazing talk. For me, at least, I hope there would be questions from people. I don't see any raised hands at the moment, so I'll just gonna go with mine because I had a few. First thing I was gonna ask is, okay, we have a question from Katya again, so I will just skip my questions to the end then.
Oh, you could ask. Okay, thank you again. I just wanted to ask, what was the initial motivation for choosing such a low frequency? I mean, it's really really low. So
yeah,
did you expect that you would make this Oberhauser MRI? So this was the motivation, or what?
Yeah, so I guess I'd say that my work there is really around the contrast agent imaging. So I came into that lab when really things were ramping up in the human brain imaging. The reason for choosing such a low magnetic field was that initially the scanner was actually built for hyperpolarized xenon MRI. So I'm not sure if you're familiar with hyperpolarized xenon MRI at all, but basically the idea is that you hyperpolarize a gas and you inhale it and perform lung imaging. And with xenon, you can get close to 100% spin polarizations. And what you find is that when you hyperpolarize the gas and you get 100% polarization, field strength doesn't matter to your signal to noise anymore, because you've already polarized. You don't need your field to polarize. So I guess the answer is yes, it's very low. But when you're performing truly hyperpolarized imaging at large polarizations, it doesn't matter.
Okay, thank you.
I had a question related to that. With the Oberhauser effect and imaging the nanodiamonds, what's the irradiation frequency that you're using there?
Yeah, so for the nanodiamonds, for the nanodiamonds,
for the nanodiamonds.
So for the nanodiamonds, it's again 6.5 millitesla, 276 kilohertz on the hydrogen, and then on the electron side, it's 190 megahertz.
So at 1.5 Tesla, that would be in gigahertz range, right?
So at 1.5 Tesla, it'd be about 45 gigahertz, I believe.
45. Okay, that's probably not suitable for the patient for clinical imaging, but for some samples that might be an interesting thing, because I think we had some people do working with nanodiamond with NV centers in here. Maybe they would be interested in that. I should probably speak to them.
Yes. So we actually did it at a similar experiment at X-band. So I think it was 330 millitesla, and it was a 9.8 gigahertz system, and we did see some effects. they weren't as pronounced. And the reason for that, as I kind of showed a little graph quickly but skipped through it, is that the effective coupling strength is much lower is much higher at the low magnetic fields.
Mm-hmm.
So because the correlation times are actually quite long, the lower magnetic field allows you to see those long correlation times.
So how much of this, how long does this hyperpolarized state live on? Because how much synchronization?
Yeah, so interesting question, and I'm not sure whether, I mean, I imagine you've seen a bit about hyperpolarized imaging and MRI, carbon-13 stuff in the MRI community-ish. Yeah, so let me, there is a whole section of my talk that I cut out about hyperpolarization because most of my PhD was actually at 3 Tesla using a hyperpolarizer that operates at 3 Tesla. There is an entire separate body of work that aims to hyperpolarize carbon-13 molecules. And so specifically, people are interested in things like pyruvate and urea, things that are metabolized by a cancer. And so what these systems do is they hyperpolarize the tracer or the metabolite. And then what you do is you inject the metabolite and you watch the metabolic conversion via carbon-13 MRI. Now, these systems have something like pyruvate, lactate, urea. The T1 of those is about 10 seconds. So you have no more than a minute to image whatever you want to image. On the Overhauser effect, what you're actually looking at is a water T1, so a hydrogen T1. So you're talking about a polarization that lasts sub-seconds.
Yeah.
But because you're doing the hyperpolarization in situ at that 190 megahertz, that doesn't matter because you can just keep driving polarization. For these carbon-13 studies that I'm talking about, so what they do is they typically perform, they're about 3 Tesla, so 90 gigahertz, and on solid samples where you don't have to worry about the essentially heating the water, your dielectric effects. What they do is they hyperpolarize a frozen sample, then rapidly thaw it and inject it, and you have about a minute.
Yeah,
the reason that
I've heard about that technique.
Yeah, so the reason that I'm saying all this is that the actual original start of all this nanodyne work, and that's what I cut from my talk, what we were looking at doing was hyperpolarizing the carbon-13 nuclei within the diamond itself. And so that's something that we did, and we showed that you can image the nanodiamond via the carbon-13, and diamond has a T1 of order an hour. So that carbon-13 signal lasts of order an hour. Okay. But for those of you that really know your imaging, your MRI, the downside that is your T2 in a diamond is about 2 to 3 milliseconds. And that means that your ability to image it is really strongly hampered.
Yeah, so, but so you probably use some ZT or UT sequence or something like that.
So we used, I'd just say we use short TE. I don't know that I'd call it ultra short TE. A lot of the clinical, I would say that a lot of the clinical systems don't even let you pulse short enough for the how long our lifetimes were, I guess. But we tried to push the TE as short as we could.
Yeah. So we have a question from Pavel Seregin, right?
Hello, do you hear me?
Yep.
Okay. Thank you very much for a very interesting talk. So I have 2 questions. First question about discussion. You mentioned that there is 3 direction, new hardware, new acquisition, and new contrast. And can you explain in more detail what new hardware we can use for such low field MRI? It's a first question. And another question about noise inside the coil. You mentioned that SNR is limited by thermal noise, not body noise. And we will know that in 1.5 Tesla, for example, the thermal noise is very low. So can you explain in more detail what is techniques? Exist some techniques for reduce thermal noise in low field MRI? Maybe noise reduction techniques or other techniques? Thank you. Okay,
cool. I'm going to try and remember each of those questions, and if I missed one, let me know. I probably missed. Yeah. So starting at the end around thermal noise versus body noise. I mean, I guess probably in terms of, I'm not sure if you're really asking for an explanation of why it's the case that thermal noise is more significant than body noise, beyond, I guess, saying that you're at a factor of 200 less in field. And that means that the body loading on the coil is almost non-existent. So in practice, when we just don't get coupling between the coil and the person, when we tune up these coils and we build them, we often don't even look at the loading till we're ready to use them, and we just do a quick check. Yeah, I guess in terms of like, how do you reduce the coil noise? The problem, as I said, is that you still need to maintain that imaging bandwidth for the readout. So what you can do is you can actually cool the coil. So one of the ideas that people have done is, say, put a coil in a liquid nitrogen bath to boost the SNR. And that works, but it's also not really in the spirit of making a system more portable. So it's something that we haven't investigated further. On top of that, you can also use you can build, so that coil that I showed you and the images I showed you are all with a single channel coil. So you can build sort of a conventional quadrature coil, and you can also build, so there was a postdoc that I worked with who built essentially a parallel imaging 8-channel coil. But what you find in that case is that you don't win by performing parallel imaging, because if you're going to acquire K-space, you may as well acquire all of K-space. You're not trying to accelerate an undersample. In terms of the hardware question, I guess what in terms of new hardware, I think really what it comes down to is, how do you make, if you can relax your constraints on magnetic fields, there are all sorts of other possibilities for your hardware configuration. So what I showed you in that talk was of a sort of it's not a Helmholtz coil, but it's similar to a Helmholtz coil. 2 kind of rings is an electromagnet creating a main magnetic field, and the electromagnet. If you want to go to slightly higher magnetic fields, what you find, than that 6.5 millitesla, what you find is that the heating and the cooling requirements of the electromagnet become prohibitive. So above that sort of 10 millitesla, 20 millitesla, what you'll find is that people shift to permanent magnets. And so the commercial systems are typically, so the hyperfine system I showed you is based on a biplanar permanent magnet system. But there's quite a few groups out there now that have built systems based on Hallmark arrays as well. And so arranging permanent magnets into a Hallmark array. And I'm not sure if you're familiar with Hallmark arrays, but one of the really, so what you do is you arrange the magnets into this ring structure such that you get a parallel magnetic field within the ring. And the dipole moments of all the outside that cancel perfectly. And so what that means is that you have this really strong magnetic field that can be put essentially wherever, because it's not going to draw things into the bore. I guess, does that answer your questions? Is there another one there that I missed?
Okay, thank you very much. And what I want to expand about the noise inside the coil. So what do you think about temperature of coil? And is it a good idea to cool this coil? Did you try it?
Yeah, sorry. So I'm not sure if I
for reduce noise inside the coil, thermal noise. What techniques? For example, maybe cooling. Maybe use very low temperature for reduce with noise. What do you think about it? Did you try these techniques for reducing noise?
Yeah. So in the context of the in the context of cooling the coil, so that is something we investigated.
Improve the quality of the coil.
Yeah. So I guess maybe the point is more so that we don't actually have a challenge getting a high quality coil. So what we have a challenge is we often have to spoil the Q to get a bandwidth on the coil that matches the readout bandwidth with the gradients, so the full frequency over which we're acquiring signals. Otherwise, we cut out the edges of our images. Cooling the coil absolutely can boost the Q factor, and it can also help if you write out the mathematics of it. You can absolutely win in terms of thermal noise at a lower Q. But in terms of creating a portable system, which is really where we're oriented, we just haven't focused on that. But people have absolutely done low field MRI and cooled the coil even down to sort of like helium type temperatures and seen significant improvements in the sensitivity. So it's absolutely something that someone could do. I think the challenge is, if you're creating a clinical system, is that how do you integrate that with everything else you're doing? But absolutely a future system might do that.
Okay.
Thank you.
Yeah, thank you, David. I don't see any more questions. I think I have some of myself by my own, but I might leave them to the emails then, because they're just some very particular things. So do you have anything to add to your talk?
Not at the moment, thank you. Thank you very much for the invitation, and thanks for your attention, everybody.
Okay, thank you, David.